Hi, I am Hadi Al-Zayer and I'm presenting our work DC2 dual camera defocus control by learning to refocus. So say you're taking a photo like this on your smartphone and you want both the person and the mountain to be in focus. You cannot do that with existing smartphones because the lens is fixed, so you have no control on the depth of field. With our method, using your hardware, we can do arbitrary defocus control post-capture. So here the image is focused on the globe. But with your post capture, we can shift the focus to be on the background, extend the depth of field, reduce it, and here we show a different example where we can change the focus plane and we can also make everything is in focus and reduce the depth of field. So this can also be used in this manner where the user can just click on wherever they want to be in focus and they can control that depth of field to be just exactly how they like. So how is this done in the past? Well, one technique is focus stacking, where you capture a photo where the camera is focused on the foreground, another photo where the camera is focused on the background, and then you merge them together, and then you'll get an image that's all in focus. But then this wouldn't work for dynamic scenes because you would get motion blur, and that would take time. Alternatively, with one capture, you can use a light field camera, and then post capture you can do image refocus or make everything in focus, but the biggest disadvantage is that you need a custom hardware which is not easily accessible. With our work, one observation we make is that now most phones have more than one camera. Then the ultra-wide camera has very deep depth of field, so everything is in focus, but on the other hand has low resolution, as you can see in the pixelated text. With the normal camera, which we refer to as the wide camera, it has much higher resolution, but has a shallow depth of field. So here it's focused on the globe, so the person is blurry. So our high-level pipeline would be something like this, where we give the model the wide image and the ultra-wide image, and then the target or desired depth of field, then want to match the wide image with the desired depth of field. The problem is, how is this image supposed to look like? We cannot actually control the depth of field of the smartphone, so we don't really know how the grand truth is supposed to look like. So how would we collect the training data? Because the smartphones have fixed aperture. Ideally, we would want something with variable aperture, just like you'd get with DSLR, but we don't want to use a different camera to avoid the domain gap. So our insight is one related task is image refocus. So here, say you have refocus network. You give the input image, you tell it what the input focus plane is, which is here on the foreground, and then you give it a target focus plane, like on the background, and it will do image refocus for you. It will refocus on the background. Well, you don't need to give it explicitly a focus plane. You can give it a defocus map. So here, like dark regions mean low defocus, that's very sharp or in focus, and then bright regions are out of focus. So you give it the input defocus map, which is focus on the globe, and the person is blurry, and then you give it target defocus map where the background is in focus and the globe is blurry, and to do refocus for you. So our idea is if you have such a network, you can do arbitrary defocus control by simply manipulating the target defocus map. So for example, you can scale the input defocus map by half, and then that's equivalent to making the aperture half the size and then extending the depth of field. So in our work, we use image refocus as a proxy task to make the network do arbitrary defocus control by manipulating just the target defocus map at test time. So we collect the training data for image refocus, like we collect 100 focus stacks of diverse scenes, and the ultra-wide is fixed focus, so it's one frame per scene. And since we have photos from different cameras, we can actually compute the depth using stereo, and here we showed an example depth map. And once we have the depth, we can compute the target defocus map or the defocus maps using closed form formula. And here notice that by scaling the aperture, that's equivalent to scaling the defocus map. So we can simulate different aperture size by just scaling the defocus map that we have. So the way we process the data is as following. You have the input ultra-wide image and the input wide image, and then we do flow-based alignment, and we compute the depth map with stereo, and then we'll get the align ultra-wide, and since there is some occlusion, So we'd get some artifacts on the edges, so we also generate the occlusion mask, and from the depth map we compute the defocus map associated with the input wide image. And once we process the data, we essentially give the network the input wide image, the input ultra wide, the input defocus, and target defocus. And the way it works that we have a refinement module, one for the wide image, so it does single image deep blurring or blurring wherever it can, and then an ultra wide refinement module that tries to preserve the high level, the high frequency detail from the ultra wide. And then we merge them together, and then we get the refocus, or like the manipulated image by the network. And since our model can just follow arbitrary defocus, to evaluate it, we can simply set the target defocus map to 0, and then we get defocus deblurring. So here we compare our method with state-of-the-art defocus deblurring, and we can see that since we lose a lot of information because of defocus blur, our method can do much better performance and get in sharp regions in the background compared to single image defocus deblurring, because the ultra wide provides very useful signal that's often ignored in previous methods. And since we're training on image refocus, as a byproduct, our method can perform image blurring or reducing the depth of field for us. So here we set the input as all in focus image, and we set the target to be an image with a shallower depth of field, and you can see that we get some bokeh effects similar to state-of-the-art synthetic blurring methods. And one other thing that our method can do is image refocus. So you give an input and then target focus distance, and as you can see for the bottom example here, the background or the wall is not completely sharp yet, since the target focus plane is somewhere between the foreground and the background, and our method can match this focus, the desired focus, without making the image completely out of focus. So we have fine level control on the amount of defocus that we have. On the other hand, with the baseline, where we try to do deep blurring followed by blurring, we cannot restore the level of details and match the amount of defocus that we want. So our high-level contributions are: we use existing hardware on smartphones to do arbitrary defocus control by using image refocus as a proxy task. And you can check out our website for additional results and additional applications with our method, and feel free to drop any questions in the chat or by email. Thank you.